Thank you for joining. I would like to thank the previous speakers for the very interesting talks. I'm a PhD candidate in the University of Crete and the Institute of Astrophysics Forth. The results that I will present here, some of them have been presented already in a paper of Korkidis et al. To 2020. So I will also be talking about galaxy clusters. I will also be talking about simulations. Let's see what is the turnaround radius. So an outline of the talk. At first, I will motivate the discussion on turnaround, and we will see that the turnaround radius appears quite naturally in the context of the spherical collapse model, which is an analytical model that describes the nonlinear evolution of structures. And there we will see that the turnaround radius and the matter that is enclosed there, and the density that it encloses, works like a universal cosmology probing boundary. And then I will try to compare the prediction of the spherical collapse model with actual measurements from highly anisotropic structures taken from cosmological simulations. There we will see that one can measure quite easily the turnaround radius through radial velocity profiles. We will discuss whether there is a single turnaround radius and so a single turnaround density versus multiple turnaround radii. We will do a comparison with a spherical collapse model, and then I will try to explore and explain some of the deviations we find. And then hopefully we will discuss some of the perspectives. So I've tried to keep it very simple. What are the basic premises? What does the spherical collapse model tell us? So the spherical collapse model tries to explain the nonlinear formation of structures. And we can think about it that we have a homogeneous and isotropic universe, and at some point in space, we have a point mass or in homogeneity. And we also think of the background to be expanding, and this expansion can be affected by the value, for example, of a cosmological constant. And so the collapse of the structure happens as follows. Matter that is isotropically distributed around the halo will start to decelerate from the expansion following the gravitational pull of matter. At some point, it will be detached from the expansion of the background. It will turn around and it will start collapsing towards the center. At this point, it will fall inside and eventually it will relax and it will come to a hydrostatic equilibrium. So we have two main phases in the spherical collapse model. We have the turnaround, which is of interest in this work, and we have the virialization phase, which I'm sure you all know about, and it has been exhaustively analyzed. So what the spherical collapse model predicts about the turnaround radius is that the density enclosed in this radius will have the same value for structures of completely different masses at a given cosmic time. And obviously this will be, its value will be affected on whether we have a cosmological constant or not. Now, moving to a more heavily loaded figure, if one puts the math down, then one can see the evolution of the turnaround density for different cosmological models. So if we focus on the upper panel, we plot on the y-axis the turnaround density normalized with respect to the critical density. On the x-axis, we have the logarithm of the scale factor. So early times are with negative values and positive values stand for future times in the universe from present time. And as we see initially, when matter dominates the overall content in the universe, both models that one has a cosmological constant with a black solid line. It is a concordance model. And the dust line, the dust red line, stands for an open CDM model. Both of them agree, the prediction of the spherical collapse model for the turnaround density agrees for both of them at early times when matter dominates. But subsequently, at late times and close to a value of 1 of alpha, we expect that the existence of a cosmological constant will be imprinted actually in the value of the turnaround density. And more specifically, the turnaround density is expected to asymptotically reach a constant value at late times in a lambda CDM universe, which would mean a halt in the structure growth of HelAS, dark matter HelAS, whereas in an open CDM universe, we have a continuation of that. The bottom panel plots essentially the same thing, the evolution of raw turnaround, the turnaround density, but for different values of the cosmological constant omega lambda. And as we can see already at a redshift of 0.3, the x-axis is the redshift, we can already start to distinguish between universes with different values of the cosmological constant. So hopefully this motivates the discussion on turnaround. And so in this work, we used cosmological simulations, and more specifically, the dark matter only runs of them, because baryonic effects are expected to be negligible on the turnaround scales. So we use them in order to measure the turnaround density. This analysis have been made for many simulations, but in this work I present for 2 of them. One is the dark sky simulations, which simulate a universe of 8 gigaparsecs. It is a lambda CDM simulation. Both are lambda CDM. And another one, which is the Lustrous TNG simulation, which simulates a smaller box of 200 megaparsecs with a slightly higher resolution. So the first one is expected to have lots of HelAS, and more specifically, lots of big clusters, whereas the other one with a higher resolution is expected to have slightly smaller ones. So to the main topic, how do we measure the turnaround radius? And the answer lies to radial velocity profiles, actually. And so here we see in these 2 figures 2 such profiles. These stand for individual HelAS, one for a HelA with a mass of over density 200 of 10 to the 15, and another for about 10 to the 14 solar masses. So we have a cluster and a very big cluster, actually. In the y-axis, we plot the average radial velocity. We have binned space around the center of each HelA in spherical cells. So we see the average radial velocity in each cell, and on the x-axis, it is the radius of the cell with respect to the center of the structure. With the yellow line, we see the R at over density 200, and with the red line, the turnaround radius. So the fact that we can measure a turnaround radius lies to the fact that the radial velocity profile seems to have a universal pattern if you look at it from the outside. That is, one sees that whatever happens at the inside of the HelA, for example, here it is near a statistical equilibrium. This one is a particularly big HelA, so it has a very strong accretion of matter. Whereas the smaller one does not have a strong accretion, but both of them are universal in the sense that on the outside, they both find at some point the Hubble flow, that is the expansion of the universe. So this is where one expects to see the turnaround radius. And one can speak about one turnaround radius because, as you can already see from the error bars, which stand for the standard error of the mean, the spread of the velocities there is quite small. There are many indications that one can meaningfully talk about a single turnaround radius, which unfortunately I don't have much time to discuss. So let's say we tackled the first problem of whether we have multiple turnaround radii and how we measure turnaround. Now, the second question is how does the enclosed density, the turnaround density from simulations, correlate with the prediction of the spherical collapse model? By the way, in this figure on the left, we see a projection of a galaxy cluster in the XY plane, and with different colors standing for the median radial velocity in each bin. Blue hues stand for inflow of matter, whereas red hues stand for outflow of matter. And we can already see the point that we already made previously, that on average, the velocities, the radial velocities on the turnaround radius, which stands is depicted with the red circle, is almost zero. So we want to compare the turnaround density for these simulated structures with the prediction of the spherical collapse model. And I should say from now that they do agree between them. So we would also like to see whether observed deviations correlate with the shape of the structure, or if they correlate with the presence of massive neighbors on the outside of the turnaround radius of HelAS. I don't know if I will have time, unfortunately, to talk about the third point, but let's see how that goes. So sorry, I should go back. We performed this analysis for about 500 HelAS of each simulation, and we measured the turnaround density by finding the turnaround radius and the mass of the dark matter particles enclosed in this radius. And so the results and the comparison of our results with theorists are plotted in this histogram, where in the x-axis, we plot the logarithm of the turnaround density measured from simulations over the turnaround density as predicted from the spherical collapse model for a redshift of 0. I forgot to mention, and apologies for that, that the simulations that we analyzed were at a redshift of 0, that is present time. So we see that for both models, in purple, we have the very big clusters of the dark sky simulations, and with blue, we have the slightly smaller clusters of the illustrious TNG, dark matter only run. We see that both of them are almost centered to 0, with a very small bias or an offset from theory, which is slightly higher for the TNG HelAS. So naturally, we would like to see what drives this bias, this offset. And one prime suspect is obviously the deviation of a structure of HelAS from spherical symmetry. And the reason for that is because we compare the turnaround density. Well, we compare this value with a prediction of a model that assumes spherical symmetry. What is interesting when we did such a comparison was that we did not find a very strong correlation. So what am I showing you here? In the x-axis, we see the metric alpha. We call it Esphericity Metric, let's say, which essentially is the aspect ratio of the principal axis of inertia of each halo. So a value of 1 stands for spherical, very spherically symmetric halos, whereas a value of 0 stands for prolate or oblate objects. And the value of F stands for the fractional error of the turnaround radius with respect to the predicted value of the spherical collapse model. So we see that the deviation from spherical symmetry of the matter distribution inside the turnaround radius does not correlate very strongly with the offset of the turnaround radius. And this is very apparent. Both correlations are significant, as we can see from the p-value, but the correlation coefficient is quite small and even conflicting in the two results. So this needs to be revisited, probably in a bigger sample with a higher mass range, or to rethink about the term of the shape. So the other prime suspect is the presence of massive neighbors, and unfortunately, I don't have time to dive very deep into that. But a metric we use, taken from HelAS et al. Of 2012, actually tries to see the effect, the tidal effect of a neighboring structure to a sphere, let's say, and in this case to the boundary of the halo, which for our interest is the turnaround radius. So imagine we have the halo under interest with these circles and a few neighbors. all of these small guys are virialized and their turnaround radius, let's say, lies here. So this d value actually is the ratio of the distance between the two centers, the center of the halo of interest and its neighbor, normalized with respect to the sphere of influence of the neighbor, which in this case is the turnaround radius. So a high value of the value d would stand for a small effect of the neighbor, whereas a small value would stand for a high effect. And so by doing this and comparing it again with trying to find the correlation with the fractional uncertainty of the turnaround radius with respect to the spherical collapse prediction, one finds that indeed there is a much stronger correlation between the two. Some perspectives from that one can come out of from this work is one that one should look at the evolution of a turnaround with redshift in simulations to see whether this offset between theory and observations still holds and what drives it. We need to accommodate more robustly about that and also do that for different cosmologies. And finally, how do we go about measuring the turnaround density on the sky? Thank you very much.
Thank you, Giorgo. So if there are questions, comments, please raise your hand. Manolis Pionis.
Thank you, Nektari. Thank you very much for your interesting talk. Indeed, a very interesting topic as well. My question is, I may have missed it. You may have already hinted on it. In what way do you estimate the variance of the turnaround radius that you estimate with your method?
I'm sorry, what do you mean by variance?
The uncertainty on the radius.
On the turnaround radius, yeah. So, the way in which I measure the turnaround radius is that I go to radial velocity profiles as the ones that I show here. And essentially, I find where 2 points across the zero line, the zero velocity line. And so I draw a line there and find its intersection with the zero line. And the error comes up from the error of this intersect, actually. So it will be driven by the error of the points, of the velocities. But it so happens to be so small that it's not very visible, actually. If I may, I don't know, it's a hidden slide. So actually here, I don't know if you can see this scatter plot. I compare the turnaround radius and the mass enclosed there with the prediction of the spherical collapse model, which is with the red line, and let's forget about the blue line at this point. And the different colors stand of the circles for the measurement from different halos and different simulations. So actually, the error bars are there, but they are quite small. You can actually see it here, the error in the turnaround radius. In the mass, we don't have one because I just count dark matter particles, but the errors are very small, actually. I don't know if that answers, but that's how I get the error from the radial velocity profiles.
Yeah, well, if this is the statistical uncertainty, then in this plot that you just said, the scatter is driven by some systematic effect,
exactly,
and not due to statistical uncertainty in the measurement of the turnaround radius.
Exactly, and you can also, if you can look closely, there is a fitting line beneath the points, a black line, which is the best fit line, actually. And as you can see, it has a small offset with respect to the red line, which is the prediction of the spherical collapse model. So that's what we tried in this work to tackle, this offset problem, by looking at the shape of structure inside the turnaround radius and the effect of neighbors. And as it seems, the effect of neighbors on the outside seem to be more significant.
Right. Sorry, I don't want to inhibit other colleagues, so I will stop here. And if there is time, I will ask you further below.
Yeah, sure.
Further.
Okay. So Marios Kalomenopoulos.
Hi, George. Thanks for the talk. I had a quick question. So, do you think that if you include simulation with baryonic effects, this is going to change the result at all?
Well, I don't think that that is the case. And the reason for that is if we were discussing the virial radius, for example, the virial radius is a little bit smaller than this black circle that you see here. If we were discussing that, then baryonic effects could play a role, and we should have a look at that. But as you can already see, this is, by the way, the colors stand for particle density. We don't have much particles around the turnaround radius. So I don't think that baryonic effects would affect it there. Baryonic effects are expected to be more dominant on smaller scales. For example, if we wanted, aside from the center of the cluster, to see a subhalo, as this one out there or this one. I hope that answers the question.
Yep, thanks.
Manoli, if you want to continue, we have 2 or 3 minutes, let's say.
Okay, very quickly. From what I understand, the turnaround radius is an average measurement. You assume sphericity, and of course you get the radius. In reality, as you can see in this plot that you show, it's actually a surface that defines the air, because some parts will be collapsing faster than some other parts. So in effect, I mean, I'm not sure that this can be done, but I'm just asking. Could it be that taking into account the fact that you don't have a nicely symmetric sphere to define in reality the areas that are collapsing, are turning around, but it is a surface which is complicated? Is there any way that actually could take that second order effect into account? That is, how distorted from a sphere is the surface of the turnaround area, and could that be an indication, for example, that could provide you with a more let's say sensical measurement of the uncertainty that the radius has?
So if I may try to answer that more indirectly, this is again, and we are at a nice point here. This is the problem, if I understand correctly, of a single versus multiple turnaround radii. Another way, of course, one could think of a different shape that would exactly capture the behavior of the turning around, but that shape would not correlate probably, or would not be we would not be able to describe it through the spherical collapse model, which is quite simple. So another way to look at that, whether we have multiple turnaround radii, is to divide the sphere around its halo into different directions, into hemispheres, let's say, and see whether one finds a significantly different values of the turnaround radius defined similarly in different different hemispheres. Well, I have not included that, and it is not published yet, but I can already say that the effect is not very significant. And in the cases that we do have, let's say, multiple turnaround radii, still a single turnaround radius will well, these different turnaround radii will not correlate. These structures that have that qualities, they will not necessarily deviate from the predicted value of the spherical collapse model. So this offset that we found did not correlate very much with different turnaround radii. I hope that indirect answer helps.
No, the answer is quite nice, actually. What I suggested, however, and I just finish here, is that maybe if you do, as you said exactly, for example, divided in quadruples or in semi-hemispheres, you could get a better estimate of the uncertainty of the radius. Not to use that, still use the spherical collapse model and the spherical turnaround radius, but have a better estimate of the uncertainty. Okay, thank you very much.
Yeah, sure. Thank you.